We're now going to look at the different types of muscle fibers and the structure of them. So there are three types of muscle fibers. You've got type 1, type 2A and type 2B. Type 1 is known as slow oxidative. Type 2A is known as fast oxidative glycolytic, and type 2B is known as fast glycolytic. And these three all differ in many ways. The colour of each differ. So the slow oxidative colour is red, as it has it's small, it's the smallest one of all three, and it has a high capillary density. So a lot of oxygenated blood is traveling to that muscle fiber, so will be very red, as oxygenated blood is red, so it will have a red color to it. Type 2A is also red, as it still uses oxygen, so it still relies on oxygen partially, so it will still be red like the slow oxidative muscle fiber, but it won't be as strong a red as it has a lower number of capillaries, so would have lower amounts of oxygenated blood traveling to it, so would be a lower lower shade of a weaker shade of red. The fast glycolytic muscle fibers, however, aren't red. They are white, and they're white as they've got a very low amount of capillaries traveling there. So there's a little amount of oxygen, as it doesn't require oxygen, as it mainly works anaerobically. So it doesn't have that oxygenated blood flowing to it, or as much oxygenated blood flowing to it as the other two muscle fibers, so it would be more of a white color to it. The fiber diameters also vary, with the type 1 of the slow oxidative muscle fiber having the smallest muscle diameter. This would be because it produces the least amount of power over a long period of time. So since it's producing a little amount of power, then the fiber diameter would be small, as it doesn't need a big size to create a huge amount of power, as it's only creating a small amount of power. Fast oxidative glycolytic muscle fibers, or FOG muscle fibers, have a medium diameter, as they produce a medium amount of power compared to the slow oxidative and the fast glycolytic. So would have a medium fiber diameter, as this here is proportional, as seen in the slow oxidative. And so the fast glycolytic muscle fiber must have the largest diameter, as it's producing the highest amount of power, so needs a big volume to produce all that power. In the slow oxidative muscle fiber, there are actually very few muscle fibers per motor unit. So the motor unit is each motor neuron, how many muscle fibers that motor neuron is connected to. So in a slow oxidative, usually it's about 10 to 18 muscle fibers that's connected to, whereas in a FOG, fast oxidative glycolytic muscle fiber, there's a medium amount of muscle fibers per most unit. So that a fog would have approximately 300 to 800 muscle fibers per most unit, but that would have more proportion towards the lower end of that, so towards the 300 amount rather than the 800. And the fast glycolytic muscle fibers would have the most muscle fibers per most unit. And that would also be about 300 to 800 depending on the person with genetics, but is the highest out of the three. And this is because with the fast glycolytic muscle fibers, you're wanting to create the most powerful movements when they're recruited by the body, by the brain. So if you want to create the most powerful movements possible, or just a very powerful movement, then you're going to need a lot of muscle fibers per most unit to use a greater proportion of your muscle to accomplish that powerful movement. So it makes sense for the fast glycolytic muscle fiber to have a high amount of fibers per motor unit compared to the slow oxidative muscle fiber, as the slow oxidative muscle fiber only produces weaker movements compared to the fast glycolytic. The number of capillaries, the number of capillaries of each muscle fiber varies. So the slow oxidative muscle fiber would have the most, as it's relying mostly on, well, purely on aerobic respiration, so needs that oxygen supply to run properly. So we need a high proportion of capillaries, and that is also why that the slow oxidative gets that red color of it. But yeah, so the fast oxidative glycolytic muscle fiber, where obviously it still works aerobically, so still has a high amount of capillaries, but obviously a much less than the slow oxidative, as it's much larger and doesn't rely on aerobic respiration as much, as it can also work anaerobically. So doesn't require oxygen when working anaerobically, so doesn't need a constant oxygen supply, so only has a smaller number of capillaries. And finally, the fast glycolytic muscle fibers have very low number of capillaries, as it only works anaerobically. But obviously still needs some capillaries to supply it with oxygen, so it can still work efficiently. But yeah, as it works anaerobically, it doesn't require much oxygen to produce energy. The number of mitochondria. Obviously the slow oxidative muscle fibers would have the most mitochondria in them, as the mitochondria contribute to ATP production, and that can be done through via fats, glucose, or amino acids. But for this to take place, there must be oxygen. So that is also why there's a high number of capillaries in slow oxidative muscle fibers, as those two link together, as the capillaries are supplying that muscle fiber with the oxygen it needs. This means that the fog muscle fiber would have the next amount of mitochondria in them, so it would have a less than slow oxidative, but more than the fast glycolytic muscle fibers, as it still has a reasonable amount of capillaries to it, so it can still use it to produce ATP. But as there's less capillaries, that means there's less oxygen, so there would be less mitochondria producing the ATP. And also, this is done because it can work aerobically, but also anaerobically. So if it was working anaerobically, it wouldn't have oxygen to work with. And finally, the fast glycolytic muscle fibers have low numbers of mitochondria as it's working anaerobically, so it doesn't have oxygen supplying it to use the mitochondria to produce ATP. As it is anaerobically means that it's working without oxygen. The number of myoglobin also is similar to the number of mitochondria. So the slow oxidative muscle fibers would have the highest number of myoglobin, as the myoglobin is used to hold on or store oxygen, and which then can be used from those stores when needed. So when the muscles have been working for a long time and are running low on oxygen, as the heart rate is so high, it's working so hard, it can use oxygen from the myoglobin to supply it to the slow oxidative muscle fibers to keep it running efficiently. Similarly, the fast oxidative glycolytic fibers also have some myoglobin, but not nearly as many as the slow oxidative, as it can work both anaerobically and aerobically. So with aerobically, it will have myoglobin to supply it with oxygen, as myoglobin is the oxygen store, but doesn't rely on it as much as it doesn't rely on aerobic respiration as much as a slow oxidative muscle fiber. And then contrastingly, or similarly really, the fast glycolytic muscle fibers have very low number of myoglobin, as it's working anaerobically, so doesn't require oxygen when working, so it doesn't need myoglobin to store the oxygen. I'm gonna stop there for this video and continue on the next video with the PC stores and the rest of the structure of the 3 types of muscle fibers.